All right. Well, so what I thought might be useful to talk about is something I've just been engaged in recently with a colleague in Sydney, Len Unsworth, who has what is actually the Centre of Educational Semiotics at the Sydney's Australian Catholic University. So this was an endeavour I of course completely support. So I've lent my help there as a sort of honorary professor, and we were now preparing for a grant for application on the use of animation in science teaching. So on the one hand, this is just a report on the preliminaries of that, the early days. But on the other hand, I've been involved in thinking about animation for quite a while, in particular because I've had three actually, excellent PhD students who have worked on that. So what you'll get will relate to the question of how can we investigate the capacities of animation to represent scientific concepts, processes, and so on. So that's one of the aims, particularly also because they have in the back of their mind the use of animation in assessment. So that means we have to really know what we're doing. And if you look at the literature generally, which we have beginning to do, then there is quite a lot of literature on the use of animation in science, but very little of it actually asks the question I've just asked. The question of, what is the capacity of animation to do that? But just look at, we have here a particular animation saying, let's compare giving people some still images and some animated images, animation, and what comes out in terms of learning correctness or results. And there is one that Bernie is actually one of those incredible sort of meta papers that reviews the entire literature more or less on a very broad level, but does come out that the result of that is still inconclusive, and some people say there are also drawbacks, and we can talk about that, and I will talk about that in various ways as we go. So although of course, to be fair, there are also some people not in the immediate field of semiotics who have been addressing this issue, saying what can animation do? It can represent change of position, change of including or not including some element in the representation, or it can, and the other one said we have to look at what the representation is employed, which is not animation properly, because that's just it's still things that get to be moved. Dimensionality, of course, representation of time and continuity, and so on. But as I said before, we leave this for the moment, and when we start writing things, we'll do that in a little bit more detail. The approach, what I'm now presenting, is actually based on work that I've done with these PhD students over the past year, and that is sort of my input in the design of the project that we're working on, with a team of two people who are lecturing in science education, and two people who are more on the side of semiotics and image analysis and so on, which is myself and Len. So this is important because different, Guterres has argued, and this now we can see whether we can flesh that out, that if you use different semiotic modes to represent knowledge, the outcome is not necessarily the same, because in order to formulate or to represent things in different modes of communication, for example in animation or in language, you have to make different, he calls it epistemological commitments. So his example is very simple. If you draw a cell, let's have a science example, a verbal representation of a plant cell, he said, requires naming its elements and positioning, a relation between them. For example, a possessive relation. The language requires that. You have to say it has a nucleus, So now that's what we then know, but a representation of a visual representation requires the relative size of these things, the positioning, none of which, you might think, I know, I can answer the exam question, because I can say that there is a nucleus, but there are other things that have to be specified, but what that relation is not specified. So he thinks that this, obviously, rightly, this opens the possibility of evaluating more clearly what, if you think along those lines, you can probably evaluate more clearly what is basically going on. So now we're going into a brief overview of the tools for doing that we have been trying to develop. And these tools, the first thing that has to be said is that we have in animation two things. One is not actually the animation. That's the visual elements that are represented, and they can be anything. They can be words, they can be, anything can be animated. Anything can be made to move on a screen, whether it's words, abstract graphic elements, and so on. All these can be made to move, either to move or dynamically to change color, to change size, to change in whatever way. So that part of it is the animation. What can animation make those visual objects do? That's the core of the whole thing. It can move randomly, change color, and so on. So then we need to be able to see two things that we want to investigate in our project. The first thing is to say, okay, and that's why I said the adequacy of animation as a representation of scientific information. We need to see how these representations correspond to scientific understandings of these phenomena. We have to, and so that's what I'll come to talk about. And to assess but also, in many cases we are going to talk about, more interactive sort of ways of doing this when students get to in some way, to represent things themselves using digital media. So it's not only animations as instructive, like we've always had that with film, just a short clip explaining something with a voiceover and animation. It's also learning through doing, and that varies from games where you can make a few choices and see something change, and then to more intricate possibilities of representation. So how adequate are these softwares that teachers then use, for doing that? That's the second sort of question that I will also briefly talk about at the end, because we've done a very preliminary exploration of a software that is used very widely. We found out, by teachers in Sydney. It's called Explain Everything, and it's a sort of interactive whiteboard. You might have come across it. So I'll briefly talk about the capacities and limitations of one software. But of course, that opens up, a domain of having to look in that way at many other softwares that are being used. So one thing that we'll be doing in the project is to just find out very simply what are people actually using and how many problems do they encounter with it or not. So map that, eventually. So not unlike the book that some of you may know, Reading Images, that I've written with Gunter Kress, we start off with getting some inspiration from the systemic linguistics. Why? Because that is a form of analyzing language which is not working with things that are unique to language, units such as words or clauses or phonemes, but that's working with meaning constructions. So so in that theory of, as many of you will know, and because we talk about representation, it's especially the representational, the ideational sort of side of the theory that's important. How can we represent things? What tools do we have for it? So material processes, as many of you know, and as we also used in Reading Images, signify physical actions and events, and connects two kinds of participants. Actors, which are the entities that do the action, for example, you do something. Goals, the thing or person or whatever the phenomenon you do it to, you do something to guess, and the process, what you actually do. So you can compress a guess. The other things are there in language as well, but we can ignore them. But the point is, this crucial structure of connecting things to make meaning of that something is occurring, something is happening. And it can also be that there is no goal. The guess is the actor, it does something, it expands. Now, let's move to animation. So while in language, of course, these participants, going back to it briefly, are either sort of, the participants are nouns or nominal groups or pronouns or whatever, and the processes are verbs or verbal groups. But if we transfer that to animation, then what you get is the actors or goals are, the participants are these elements, whether they're words, pictures, graphic designs, anything that can be made to move. And the process, that's where the animation happens. So for the moment, this is a word. I'm now going to show you an actual animation in a second, but this is a way of saying what then happens is you can see on the screen red and blue circles, and you can see that they move in a difficult to describe way, in a random way. So you have an actor, the red and blue circles, and you have a process, they move. And then you have some representation of it, but this is only verb. But much more happens when you actually have an actual visual, which we'll see in a second. Or you have one where there is a goal, some circles, that's what you see. If you take it only on language. But now we get, now I'll show you this little video, and in particularly the second section of it, which is about movement. There are 4 bits to it. Have a look, if you can. I'll show it twice if need be. What is actually, represented visually and verbally? What is really the visual adding that verbal representation of the commentary does not describe? It's a very short segment, so it's not too hard to do. And what is only done verbally? So then we can start beginning to have a sort of little preliminary look at the differences. Here it goes. Okay.
Liquids and gases. Matter in all 3 states is made up of particles. In a solid, the particles are closely packed in an ordered arrangement. In a liquid, the particles are loosely arranged but still close together. In a gas, the particles are not arranged in any particular way.
Now the next bit.
Make up matter are constantly in motion.
In motion.
In a solid, the particles do not move around but vibrate about their fixed positions. In a liquid, the particles move around quite fast and slide past each other. In a gas, the particles move around much faster than in a liquid. They move randomly. That's
the bit I meant. You want to see it again? Okay. Because it goes that is one of the things with animation, it goes very fast, So it's complex to actually get something out of it, to learn something from it is one of the issues. Okay, we'll do it again. I think we go, I can't see exactly where, but here we go. Oops.
Around but vibrate about their fixed positions.
Oh no, it's a bit earlier. Sorry.
Slide past each other. In a gas, the particles move around.
Bloody hell. Okay.
The particles that make up matter are constantly in motion.
That's it.
In a solid, the particles do not move around but vibrate about their fixed positions. In a liquid, the particles move around quite fast and slide past each other. In a gas, the particles move around much faster than in a liquid. They move randomly. The particles have...
Okay, one more time, and then we'll just see if we can talk a little bit about it. I know... matter, that's it. I've got it right now.
Particles do not move around but vibrate about their fixed positions. In a liquid, the particles move around quite fast and slide past each other. In a gas, the particles move around much faster than in a liquid. They move randomly.
Okay, Okay, so have we got any observations about that? You know, so the first question is what is actually transmitted both visually and verbally? So he says like the particles, you know, in a solid, the particles vibrate around a fixed position, and then we have that image. Now, what has, in terms of Günter Kress's saying, you have to put, you know, actually there's more to it than what you express verbally. What other things are now added that are absolutely not expressed verbally? Let's say that simple question.
Very organized structure.
Yeah.
I mean, the particles are all of the same size and they're arranged in a very corded three-dimensional grid.
Yes, that's right. That's in the solids, absolutely. Anything else? Yes?
Coordinate system is visualized.
They have a coordinate system in there, so you could then ask, is that another way, in another mode of, I'll come to you in a second, is that in another mode to say in a fixed position? You know, it has to be done in quite a different way, and actually in a sense more explicitly. You know, sorry, what were you going to say?
And the particles are round like balls.
Yes. Yeah, they're balls.
With the glass surface.
Yeah. So is that what particles are like? You know, this is what we have to ask. Because you have to commit yourself now to giving them a physical shape. And they're round, they're grey, obviously they're somewhere where there's a bit of light on them, you know. And not only that, there's another thing. There's one other thing that is, you know, clear about it. This that thing of vibration. In the words it says they move around a fixed position, right? But we see them moving. And we see that movement is happening at a certain speed, and it has a certain reach, expansion, you know. And even stranger, the whole thing is coming towards us. Did you notice that? The whole thing is coming towards. Now, is that important or not? You know, is that important or not? Can that, you know, do we have to think about that? I had. We'll come to talk about it a bit later because I got another clip which I won't get the same trouble with. But that has to be kept in mind. You know, a whole lot of things are being now specified. You know, and the same applies to the other two bits. You know, but there's one thing that the words do that the images don't do, and that's sort of names, solid, liquid, gas, you know. You see a phenomenon and its name. So there is obviously an interrelation between what they do. The particles and the particles move around, you know, on their own at a certain speed, and they have. What about in this last thing, you know? But in the liquid and the gas, you know, then we get these little sort of a few dots to sort of show the trajectory. What can you, if you want to learn something about, you know, in the words it says they slide past each other, and then in the images you get that thing. What does that respond to? What can you learn from that, you know, or not? What is that trying to tell you visually?
It's trying to tell that the objects are actually moving.
Yeah.
I think it's also trying to show at least that it is a randomly.
Yeah, that there is a sort of trajectory. But
But it's trying to show. That's what it's trying.
But you still have to figure out how the gas is more random than the liquid, in my opinion. You know, I would ask that question. So, and yes.
Yeah, for me it was disturbing that there was a contradiction because they were saying it's moving much faster,
Yeah.
but the dots are drawn in the same pace on each picture, so
Yes.
I don't get the sense of something being faster.
Yeah.
So that's a contradiction.
So if you know, obviously you learn from the words and the things together, but yeah, there are inconsistencies. And so that's what we're starting to try and explore, and what an example like that, a simple example like that already shows. Carrie Jewett, in a book that was written now something like 15 years ago on science teaching and technology, you might have come across it, has a wonderful example of that kind. A game actually called Playground that is supposed to teach you about mechanics. And so the bits she describes, I've never played the game, but she describes how they learn something about bouncing. And then you can choose between different pictures, and one is a picture of a ball and one is a picture of a spring. And then you can choose that, and then you see the bouncing happen in front of you. No words whatsoever. However, she says, quite rightly, the problem is, what actually does the bouncing? Is it the ball or the spring, or is it the bar that they bounce off against? You cannot tell. So there can be things that look. You're saying, now I've got a simulation of the real thing in front of me, but to understand it scientifically is point two. And then of course some explanation of that or some other thing would be necessary to do that. So that's sort of my first point here, to think why that's interesting and important to do. Now, then we get a second stage, because the other thing about animation is that it does, essentially there are two key things that happen. If you start from animation, one is this movement that we've just explored a little bit, and the change. And it can change, animation can make them change in any sort of way. It can make them bigger, smaller, it can change color, it can change any sort of aspect, visual aspect of the things on the screen. It can even completely change a thing in something completely different. All that's possible, and that is obviously in principle one of the powers and sometimes the magic of animation. So we can continue to have some inspiration from, but also some differences from Halliday's theory of transitivity here as well, because so I'm saying in language you have certain processes which are not about display movement or action or something that happens, but about states. And so you can have a gas has no definite shape, and these are called relational processes, where you have an object that's then referred to as a carrier that has an attribute of some kind. The earlier example, with a cell has a nucleus is another example of that. Particles are close together. So that is what is a similar but different thing in language. Well, first of all, in language, and that's relational clauses, can represent changes, because you can have it is clear, or you can have it becomes clear, or it turns into something else, etc. But in animation, things are always dynamic. It is not holding still. Then it's not animation anymore. So that relates to the difficulty of seeing it that we just mentioned, because sometimes you just have to understand and look carefully. You have to hold things still, and then the process is not there anymore. And so that's why we had to see that slide, that little tiny sequence 3 times, and probably even that was not enough to observe the kind of things you might like to observe. So if you were to use animation, I say to Len, and particularly to the science teachers who are very enthusiastic about animation, you have to take this into account. If you're going to give them a little short animation as part of some kind of assessment, how often do you have to see that to be able to actually work it out? Important. So in animation, attribution, if we still call it that, is all dynamic. It can elements change their form, size, color, or brightness. So here is that is something that sort of translates part of one actual animation. Blue solution becomes pink. But of course, if I showed you, I'm not going to show you all these clips, and I'm glad I don't, because that would be a lot of extra. But you can imagine that you then obviously have not only the solution, but also that it's in a certain vessel, and and so on and so on. that it has other qualities, and why that's important we come back to shortly. And then there's another thing, you know, you have that in linguistics you can take inspiration from the idea of linguistic construction that identify what something is, the identity of it. Boron is an element on the periodic table. Okay. This process is called condensation. So there, again, identity, what something actually is, rather than what attributes it has. This is an important distinction. That also in animation. That is again always dynamic. It's not that something is, it's that something appears or disappears. You're going to see a few more examples. Appears or disappears. So, as we know, animation can totally also change identity. Can change words into images, images into words, if you so would like to. And so that leads, again, that the same phenomenon, something that's scientifically the same phenomenon, can sometimes be represented in terms of identity and sometimes in terms of attributes. For example, well, in one animation, the change from liquid to gas was represented as the same as a change. It was not a new one as the one we just saw. The same whirlwind of, you know, the same particles suddenly began to move faster, and then the commentary said now it's changing into gas. In another one, they just had a total change. They had water in a bowl, and then suddenly, mysteriously, there became a white cloud about the bowl, and that had to explain, you know, the change. So that's a complete change. There are two things we can. It's closer to experience, you know, because water, you know, that's better in advance, I don't know, and you can see some vapor or some damp or something that's like gas, but it is not actually represented in the same way. And having these tools make us able to actually put our finger on it and have some ways of identifying these issues. That existential processes then also are there, but again they're dynamic. Things appear or disappear. They never. So one animation represented gas in the form of blue balls in a jar, much like the blue balls or the gray balls we just saw. The jar then entirely disappeared and made place for larger blue balls which moved in a different background. So yeah, things completely disappeared. So that's the part of trying to explain to you the tools, you know, and I'm quite happy to pass on these slides if you want to look at them again and look at these examples up on your own. You know, that would be probably helpful, you know, because like animation, this too goes very fast. So we basically then recognize 4 types of animation processes. Movements, where elements change position or move in place like in the solid, or change position like in the gas in the liquid. Changes of attribute, where elements change in shape, size, color, and we see some example of that in a minute, or brightness. Changes of identity, where words change into images or vice versa or whatever, where jars of water change into clouds, you know, for example. All of these can, and then changes of inclusion, where things just appear or disappear, and then they can affect the whole screen, a whole element, or part of an element. So in the good old tradition of the systemic aspect of semiotics, sorry, that's too fast. There you have it. You know, so you have movement, change, and inclusion. As here you have the little toolbox in a sort of overview. Movement can be transactional. There is something does something to something else, which makes that something else change in some way, or non-transactional, which can be that something just moves but not affecting anything or anyone else, or that it moves in place, like the solids, you know. So there's no actual displacement, and so on and so on. So you can see these are the things we've discussed. There's a bit here again, a small bit that I want you to pay particular attention to, and I'll tell you when it comes. This is actually made with explain everything.
The horizontal windshield is vertical. The stronger of the two vortices becomes the main force of the thunderstorm. strong wind at the top of the storm draw warm air from the bottom, while cool air from the top will force down. This is called a mesocyclone. And this way creates tornadoes.
Now, this bit.
Tornadoes throughout the world is quite high. Very few remain in it. The weakest tornadoes can break branches on trees and perhaps do light damage to homes, while the strongest tornadoes can completely destroy entire buildings.
Okay. Got it? Yeah, so I'll show it one more time. You know, now and then I'll tell you why I want to show it. Here we go. Upsy daisy.
While the amount of tornadoes throughout the world is quite high, very few remain harmed. The weakest tornadoes can break branches on trees and perhaps do light damage to homes, while the strongest tornadoes can completely destroy entire buildings.
Okay, so if we use our little tools, then what has happened is first a non-transactional action. Because this branch of the tree simply breaks off. There is nothing to be seen of why and how it breaks off. It just breaks off, could be any reason, you know. And that's what it is. Then in comes a tornado, you know, and we can also talk about the movement of the tornado, and it's interesting that we can compare the bit of the video of an actual tornado and that. But then the tornado moves around, and so the tornado does bump into the tree, and the whole tree falls. So we get two explanations of this. We get two different things. You know, we get something happening non-transactionally. You know, if you of course you can say, well, it's meant to be this and that. But if you're really serious about you know, representing these things visually, and what the best way of doing it is, then you have to say it has this damage, because the commentary says, you know, tornadoes do sometimes minor damage and sometimes big damage, you know, has to be caused by the tornado, you know, and by the impact of it. Still, that you get this sort of impact of a physical object, you know, a quasi-physical object, however diaphanous it is represented, you know, it's a little bit see-through-ish, you know, transparent-like. So again, you'd have to say, okay, like now, what is our understanding of how this process happens and how tornadoes move? Because if you look at the other one, you know, you see, and even with the arrows, you can see there is the key is this upsurge, you know, and it stays in a particular place where all these forces come together, even, you know, so. Again, you know, there's an animated representation that you have to, and the science teachers that the lectures and so that, you know, when we talk about these examples here, they're often very surprised because they haven't yet gotten into the habit of saying, you know, of doing what I am supposing we should be doing, which is you know, knowing enough about visual communication and animation to say, like, this is not maybe the best way. If not, is there another way we can do it? Is there another sort of type of movement we have to use, you know, and another form of representation? Okay, that was the tornado. Okay, so that was my summary, you know. What do we see? A small branch breaks off and whirls in the sky, non-transactional process in my terms, you know, with branches acting. Next, the tornado appears suddenly out of nowhere, you know. There is no causal things like, you know, the concurrence of forces that make it happen. It just appears out of nowhere. It walks like an actor on the stage into, you know, onto the stage, and touches the tree. Transactional action with the tornado's actor. Thus the same phenomenon, Theo concludes, happening in two different ways. So now there comes a second part that is also important. Oh yeah, we'll have time for that. All these processes can be realized in different ways, you know. And we've already touched on that. For instance, the movement of gas particles can be fast or slow, you know, to different degrees, more or less regular or irregular, you know, all of these things. Soon as you represent it visually, we have already seen with the earlier example of solids, liquids, these other qualities come in. And they're not easy to represent in the form of an either-or binary model like I showed at all, because they all happen at the same time. That's very unlike language. That's like what happens in a visual, you know. So, and it happens not only with the visual aspect of it, but also with movement qualities. They cannot be captured in systems of binary distinctions. They are all happening at the same time. There is always a certain, if there's movement, there's going to be a certain speed and a certain extent and so on. So here are the ones we come up with. Direction, the movement goes up, down, right, left, everything in between. We already criticized the movement of the tornado in the animation. Directedness, does it take the shortest route to where it goes, or is it meandering? Well, the tornado was meandering quite a bit, And is that meaningful? Is that actually telling you something about tornadoes? No. But it is there on the screen. Expansion, taking up maximum to minimal space, like obviously that's clear in the case of gases and liquids. Velocity, how fast. Force, the degree of energy or vigor of a movement. I didn't think for example, I saw the tornado sort of like almost sort of danced do you agree? Graciously into the screen. It wasn't sort of coming in like strongly at all. Angularity. It was also quite round. It made nice round movements. All of that is obviously observed by anyone who observed this video. And do you do something with it? Yes or no? Fluidity, smooth, unbroken movements to breaking up into steps, and regularity. All of these can vary during what my student Joshua Hannes called an animation phrase. So that's the equivalent. That's the equivalent of one particular action happening, like movement in space. And they can happen in at different levels. So So if they are not, and this is my point, the last point really that I want to make. Hopefully we have enough time for that, because we started a bit late. So then, we have all sorts of possible, when there is no scientific resource, we have all sorts of other resources to interpret these movements. And my slightly flippant example of the tornado sort of dancing in on the stage is a good example. I relate it to experience, to what I have seen in the world that moves in that way, what kind of movements that I know, move like that. So we can either do that on the basis of some kind of recognition, it reminds of a certain kind of movement, which has certain qualities that has nothing to do with the scientific, thing, but still comes in. But maybe it has, maybe sometimes it has other intentions. Or we can do it on the basis of our physical experience as moving bodies and circumstances in which our movements display certain qualities. So meandering, for example, it depends on the context what it is. It can be because you are drunk, or it can be because you are not knowing where to go, or it can just be because you think it's nice to do. There are many contexts for it, but it has meanings. We can make meaning of this on the basis of experience, and Christian and I have often talked about these forms of meaning making.
Viruses spread when you cough and sneeze, and the tiny droplets land on surfaces others might touch. You can help reduce the risk by coughing or sneezing into your arm or a tissue. Bin the tissue. Wash your hands with soap and water. And if you're sick, seek medical advice. Together, we can help stop the spread and stay healthy. Visit health.gov.au.
Okay. What I wanted to say about this, and I'm going to show it again, but I'll first give you a little bit of a sense of what we can now observe, rather than look at my. Luckily, I've got the print out of this, so I don't have to go back and see. And then the last thing, still, we have to explain everything. So can we have another 10 minutes or so?
Sure.
Yeah.
I think people are here to see you.
Okay. Yeah. All right. Okay. So first of all, in this video, you will see many examples of change of size. Because you will see little droplets, little viruses coming out of the mouth of the coughing boy, growing in size into a huge cloud. You see disappearance. You see little droplets falling from the cloud on a table, and then a hand moves in and gone. Poof, table is gone. This happens all the time. You see appearance. Suddenly a group of 5 people appears as though they're being drawn for you on the screen. Plus viruses, now quite small, hovering around them and between them, you know. And I'll say some more about these viruses in a second, coronaviruses. And then after a while, these viruses change into white crystals. So total change of what they are. So obviously to signify that they have been conquered, you know. And of course also, you know, change of color. You know, a girl is coughing into a white tissue that changes pink. And we see movements going of the movements of the viruses in various directions. First of all, when it's dangerous, when the boy coughs, they go upwards and expanding, you know. And then later on, when you see the 5 people, they're just hovering like mosquitoes in between the people. You know. Now this is very interesting because, you know, like in Australia, you can actually there's a channel in the multicultural channel where you can look at news from many different countries. So I looked at, and they all for a time had in the background, you know, on the screen, viruses hovering around. And in different countries they had different colors, you know. Sometimes the spikes were very spiky, sometimes not. Sometimes they moved, in the Dutch one for example, they moved gradually like this, you know, onwards and onwards. You know, in the Australian one they menacingly hovered around in place. You know. So these viruses behaved in many different ways, all of which have very little to do with the actual viruses and an understanding of what they are and how they move along the lines of what we just looked at with the gases and the liquids. But all of which have other meanings, you know, because like obviously to hover into place can be menacing, you know, what is going to happen, and to steadily move on and grow, you know. These have meanings that are of a different kind, you know, and that is what can happen. Even in when you have these. Well, so now I'll play it one more time, so you can again see these phenomena unfolding.
Viruses spread when you cough and sneeze, and the tiny droplets land on surfaces others might touch. You can help reduce the risk by coughing or sneezing into your arm or a tissue. Bin the tissue. Wash your hands with soap and water.
And it disappears.
And if you're sick, seek medical advice. Together, we can help stop the spread.
And now we have they change into pluses.
Hey you, authorised by the Australian Government Canberra.
Yeah. So I just think that, you know, an alertness to these things can do some work in seeing what actually goes on, you know, and then also to ask, well, what is telling us, what is it, why is it, you know, in this case, of course, it is not really to explain to us exactly, you know, but to warn people to have these behaviors. Okay, now we come to the last little section of what I had planned to do. And we go to here. Oh, the coronavirus, we've said that, you know, I've already said it. So just a few words on explain everything, you know, so that we also have at least some first indication of the kind of materials where students themselves can do things. So this is my PhD student Yufei Hai, who's now back in China and finished her PhD brilliantly. We studied the affordances and limitations of concepts taught in junior high school physics. So we looked at the curriculum and we saw how does this explain everything? How is it able to represent that as a tool, as a built-in semiotic potentials? Which of the types of movements and directions and so on that I've just explained to you can it actually represent, and how? That was the question. So it allows 4 basic operations, I'll just do it in this way. It's a bit abstract, but, and I won't actually go in it because that takes a lot of time. But you can do yourself quite easily if you want to have a look at it, how the interface looks. But the point is, it's an electronic whiteboard, so you can draw on it, and you can record what you draw and replay it. That's the first point. Then you can import, and you saw that in, obviously in that Explain Everything video, that you can then import import videos, like the one, the active video of a, and you can write on that, as they in fact did in that thing. Very simple. They modify these, and you can modify these as well in various ways with the limited, but nevertheless, of using a touchscreen. You can add further animations to an existing animation. You can always go over it again. And there's only one other thing, which is called auto rotation. So you can make things move, and you can change that movement in terms of radius and speed. So what we did was to say, okay, hang on. Because the reason is it's always something that I wanted to be on the whole screen from current slide. There we go. And so this is a sort of summary, of how you can do these various things that we've talked about. You can material process position. Yeah, you can do that. You can drag, as we can on screens. Movement in place, you can do that, or you can use auto rotation, as well as that. Change of inclusion, yes, you do that by drawing, by inserting and deleting. So all these processes can be represented, in this particular, through this particular technology. And children can do that, and it's not so difficult. You can change the shape, you can change the size, change of color, change of luminance is not really possible, but that's, But there are still, so that's just a way for us to try and see, well, when we've explored what you ought to be able to do to have a reasonably, accurate representation, could be done there, but it is not always easy. There you come to the point. For example, let's take our examples of the movement of particles in liquids. They move at different directions and at different speeds. That really means you would have to draw every single particle separately and over-record another one, which would be an enormously laborious process. So it's not, it doesn't easily lend itself to that. So this is just to end to talk to a few of those things. It's of course also very difficult to maintain a constant speed when drawing lines by hand, because that's what you're doing. Yet constant velocity, for some school subjects of science, can be very important. For example, studying the relation between mass and velocity, you need to be able to keep one variable constant to examine the impact of the other. So that is also, there are many things that are not easy to represent in a way that really demonstrates what should be going on. And it is difficult, it is not possible, in fact. You can fill the tree or the grass instantaneously with the same color all over, yes. There's a palette for that, and an interface. But what you cannot do is gradually change the color, so it's just fixed. And that can also sometimes be important. For example, one of the videos we looked at explains that in hot water dyes spread color the water more quickly than in cold water because the kinetic energy is higher. So that can be animated by a gradual change in color. You can have the two vessels next to each other. You can see that one color changes faster and one slower, but you can't do that in explain everything. So then our second point is, okay, we can use the same tools to evaluate the affordances and limitations of software for empowering learners to themselves use that medium rather than writing, to represent what they know, in a way that that can be assessed if perhaps as being adequate, and that's that word, adequate to what we think we would try they have to learn, about this particular process. So that's really the sort of the three things I wanted to say. But one little coda, as we, which is not directly related to science, as we were working on this totally from the point of view of animation, we began to, and particularly with my student Joshua Hahn, to say, what we found, is that moving towards a more general theory of movement that is not only applicable to animation, but also to other things. And Joshua Han, my student, wrote about dance, and found to his surprise that the kind of qualities that we had been looking at in animation, were also very strongly part of the discourse of dance in this excellent book by a dance theorist called Maxine Sheet Johnston. And a quote, she has different words, of course, but here you go. She calls aerial quality is what I call sort of expansion of movement, and she said it may be anywhere from constricted to expansive, its shape either being very small and inwardly oriented or large and outwardly oriented. When we are contrite, we shrink in size and stay put. When we run down the street with open arms to greet someone, our body is expansive, and the aerial pattern using a wide area, an expansive space, is etc. So, and that with all these different kind of things that we had discovered separately in a whole different world of dance theory, this was also discovered. And some people who talk about gestures and non-verbal communication, sometimes also come up with quite different things. For example, in one book, excellent paper in a book, there are these, they call it additional features, what I call the qualities, additional features, such as directnesses, spiral, zigzag, S-line. So, the same ideas come up interestingly in different places, as something that is something like a movement, a theory of the meaning making, how meaning is made with movement, of which making meaning in the register of science is obviously one thing that will use certain of the things we have described, as we have just seen in that example. So, time for questions.
Brilliant.
Thank you.
Thank you very much, Theo.
I was thinking, have you looked at simulations where users can manipulate animations?
Yes.
Sort of. Yes.
I mean, well, what's happened so far, and so I haven't specifically looked at it, but what happened so far is that we are collecting a corpus of animations, and yes, there are animations in which that can be done, and these manipulations are sometimes like a game, that is a very preliminary observation, that you can, for example, mass and velocity, you can sort of have different vehicles, and then you can make them, play with them, make them ride or drive, and see what happens, So that is also very important to look at, because there, I think that the same phenomena, the same kind of tools for evaluating it can apply to that. Yeah. But the example of the example from Carrie Dewey that I gave earlier on with the bouncing is what they can do. So that's how we can also look at this game. And the games are important because they also now produced, we have found, by a lot of different institutions. They are not, so the New South Wales government in Australia produces a lot, but they have not got very big resources to use the full potential of what is actually possible, because it costs a lot of energy and programming and so on. So they have little of that. Whereas, for example, there have been incredibly highly produced learning resources by the mining industry on things that are relevant to what they need, to mining. Mathematics that I talked about 4 years ago, as you reminded me, is an example where you have a digital thing that you can do things with, but you can, for example, but the actual possibility of learning together, the only thing you can do with other learners in mathematics is to compete with them. You cannot talk to them, you cannot compare notes, you cannot debrief, you cannot solve a problem together, none of those things, you know, because they are actually very much more intricate to sort of provide, and oftentimes that is not yet done, you know. So yes, that's a thing that really needs to be kept in mind, you know, from the point of view of learning, because now we go to sort of pedagogies. You know, we're going to, are we running, what kind of learning do these resources actually create? Is that a sort of, you know, transmission of information learning? Where is it on the decline from transmission of information learning to designs for learning, and, you know, on the making your learning yourself, and how much of that does it actually? So in an example like that, mathematics, it was widely used in Sydney in schools. It is, despite being a game of sorts, still has very little opportunity to discover, if you like, rather than to just find out yourself by playing what the correct answer is, if you like, yeah.
Yes. Okay, it doesn't hear it. I thought I'm going to hear my voice.
Bouncing from the walls.
So, thank you for your speech, and I got a rather strange idea. It's my field. Your research is general didactics. I'm working with. Actually, we're working with students, student teachers,
yeah.
Observing videos from classroom teaching, recorded classroom teaching, and it struck me. The student teachers have difficulties to describe what is happening on the screen, and there's a frame, and so they also evaluate and say the teacher's doing right, the teacher's doing wrong, but they are actually not cannot describe what's happening. And then I thought maybe your language could be used to describing these things.
I mean, that's a really good point, actually, that I should, because what it also does, you know, if, you know, the teachers use these materials, or if they ask students to represent things in a non-linguistic form, you know, or partially in a non-linguistic form, then you have to have a language and concepts, you know, to apply to it, and you cannot just say, oh, very nice work, Johnny, you know. You just have to actually say, you have to actually get to the point where you say, well, that's, okay, you might say this is nice, but actually, if you did it that way, you know, then the idea you have would come across even better, or whatever, because you have a set of criteria by which to look at these products, as well as by which to, you know, evaluate what you put there on the screen. And as I said before, these lecturers in our group that is working, that we're working with at the moment, when I showed examples like the tornado and a few other similar ones, and I said, look, it's actually, you know, not completely correct visually, they had not really thought of that, you know. They had sort of injected their knowledge of how it really is into this thing, you know, and so regarded it, you know, and had not actually looked at it for itself, and, you know, but how children do that, you know. And so even earlier, you know, I found in non-animation, but in textbooks, you know, partially because the graphics, the illustrations are often designed by different people than who have written the text. You know, there were often sort of strange disparities between what these diagrams or something that they really had to learn something from, you know, and what the text said. Now, when you then start to assess, you get into trouble, you know. And so we really, as these resources become multimodal, yeah, this knowledge of how to draw, and that's why comparing language and, you know, and visual is important. And we have to have the tools to do it and work with it and help teachers do that. I totally agree. Yeah, I think that's hopefully what these things are actually useful for.
Thank you very much for a splendid and interesting talk. I I wondered whether this semiotic of animation. I remember that Edmund Husserl, you know, the phenomenological philosopher, in 1937 he wrote that in order to understand science and scientific themes, you have to invest what he called the morphological structure in life world, for example bodily movement and so on, to capture this phenomenon.
Yes.
And I think that what you're starting to digging in is to explore how does this seems, and he said it has to be inexact, because it can never be totally exact. Yeah. That was a kind of a paradox, and I think you are showing us why it is so difficult to develop what we could call an adequate grammar for this.
Yeah.
So how to translate this in different areas in the world. And I figure and I wondered, do you think that we will, during the next couple of 100 years, being used to use this kind of simulation and animation and so on, will develop a more adequate grammar, or could this semiotic kind of scaffold a kind of more a grammar, so it's not so. Yeah, what you showed us was not the best example of pedagogical introduction to these phenomena.
Anyway, but yeah, I agree, and I mean, you even took a step further with my last two slides here, because in the last two slides I was just drawing attention to the fact that these ideas come up in different domains, even in the domain of bodily movement. So, but the next step is what you seem to indicate, and you know what Husserl already seems to have thought of, that how much our understanding of things is based on the body, and bodily movements of movement, and that means that you can also begin to think of pedagogies that make use of bodily movement to help people understand. You can enact processes, physically. If you, that's a possibility. I don't know, but this as a sort of as yet unexplored territory that does come up, and I think that certain things are already going in that direction. If you have examples where you just explore a phenomenon not through movement, through moving around, then in a small scale that is already happening, because your movement can be regular or irregular, and it can be this and that and so on and so on. But the whole body movement makes it even more interesting. Yeah.
Well, I will look forward to that.
Yes, well, we will think, and I think there's sort of signs of it in the literature slowly. That that is beginning to happen.
Have you looked into Leonard Talmy and you know, the American linguist? He wrote a double-bind work about what he called force dynamic.
Force dynamic.
And it's to explain how basic grammar is founded or grounded in movement and dynamics interacting.
Yeah.
And he tried to show how the sentence is built upon this kind of what he called craft dynamics.
Yeah. And that's certainly true. So but it's probably I'll have a look at that. I haven't come across it, but it makes a lot of sense, and it is another example of different, of a particular direction in which not only our thinking but also our practices are moving at the moment.
All right. So my plan has been shot to hell, as usual. One of you have one question left. Can we agree that that's the last question? And can we keep it fairly short? Thank you.
Yeah, fairly.
Fairly.
You didn't say very, you said fairly.
Fairly.
Thank you for a wonderful presentation. I have a quick comment, suggestion maybe, and a question. The first one, the comment is following actually up on Thomas's comment. Donald Schoen wrote a beautiful piece in '92 called "In Reflective Conversation with the Material." which actually aligns pretty much and pretty well with the things you've presented here today. And he has a notion of movement, seeing movement, where the students are reflecting on the very material of the things that they are producing. That might be I'm sure you already know it, but it might.
No, I don't know, but I do know the thought.
Yeah.
You know, it's coming up in different contexts.
Yeah.
You know, of our incredible ability to resonate and attune to people, but also things and landscape movement.
It
that we have, and that I've studied particularly. You know, in conversation, but that has other things as well. So, and movement is a clear thing like that. You know, that people will movements will be contagious. You know, they will be interact with other people's movements. And for example, we would actually right now we were both going like this for a moment. Yeah. Exactly mirroring this thing. Yeah.
And revealing that with that quite interested in the materiality of things, I wondered during the presentation whether you could isolate only looking at the visual components, because what we didn't talk about was the wordings, the speech, the metrics, the speed of the cutting, the music, the pitch, the metrics of what was being said, but we were looking more or less solely on the visual objects moving on the screen. What are your thoughts about isolating these pieces from each other? Can we do that?
Well, no, of course. I mean, there is, yes, that can be done, and I haven't done it. But in other contexts, I've written about that, for a long time, because it is also happening in film, and there is close interaction. But when you have commentaries of the kind that we looked at, you have to have a good interaction between the words and what you see, and through again simultaneity and coming together and merging in the impression that you have. So there's a lot of, and that is also physical. There's also time and movement and time structure in it that these two have to attune to each other as well. And if you have a commentary that doesn't do that, then it jars.
It was very clear in the governmental video. How the speaker had a specific pitch when she was using specific words, and I've worked a lot with learning videos.
Yes.
And the students often say that they prefer their own teachers because they have already decoded the teacher's way of speaking to them. So they know that when he's putting pressure on specific words, that's the word we need to remember. That's the terms we need to remember. Whether when they use videos that are spoken from other people, even though they get the visualization, they often have trouble remembering what was being said because the same notations in the speech is not there.
That's very interesting.
Yeah.